All right, start chapter 7, 7.1. Let's take a look at exponential functions. You'll see in your textbook that the format for an exponential function is y equals c to the power of x. C to the power of x. There we go. Y equals c to the power of x. Now, what's different about this, you should notice right away, is that the x is in the exponent position. And that should make sense. Exponent is kind of the root for exponential, okay? So the input value is in the exponent position. That's what makes it an exponential. What is not an exponential function would be y equals x squared. That is not an exponential. Even though it has an exponent, the exponent is not the variable, or the variable is not in somewhere in the exponent position. It could be 2x, it could be whatever. But usually for these ones that we're going to study, it's just an x, or the input variable is in the exponent position. So y to the 2 to the power of x is definitely an exponential function. So c is the constant, and that is the base of the exponent. So if you consider this a power, then this is the base, and this is the exponent, right? And this is this is a power. That's what we call it. Power, here's the base, and here's the exponent. So x is in exponent position. So let's take a look at this y equals 2 to the power of x graph. Now, maybe you are familiar with these graphs, but let's just walk it through. The easiest one to figure out is 0, and I'll start there. So x equals 0. I do have some input values here ranging from -4 to +4, but I'm going to start with x equals 0. Because when you have 2 to the power of 0, that is what? 1, yeah. Anything to the power of 0 is 1, unless the base is 0. So 0 to the power of 0 is no good. That's an indeterminate form is what it's called. But any number, variable, expression, anything to the power of 0 is always equal to 1. And I won't talk more about that right now. That's another lesson. But 0, 1 is our first point. So there it is on the graph here. I've got from sort of -4 to +4, and I've got 0, 1 as my first point. Okay? Now, if I put negative, let's go back to -4 here. So this is 2 to the -4. Do you remember what happens with negative exponents? How do you evaluate that? What does the negative on the exponent tell you to do? Go ahead and shout it out. Yeah. If you have a negative exponent, that means that that negative sign can disappear if you put the whole power in the denominator. Or if it's in the denominator, it has a negative power, the negative goes away if you put it in the numerator. So you take the reciprocal of it. That's what it means. So this is actually 1 over 2 to the power of +4. And that's 1 over 16. Okay. So 1/16 is going to be a pretty small number. We're going to estimate that's going to be right about there. All right, -2. In the same manner, 2 to the -2 is 1 over 2 to the +2, or 1/4. So this is going to be 1/4 right here. Just a little bit more than 1/16. Up to 1. Now, let's keep going. 2 to the power of 1 is 2, of course. So we got an input value of 1. We have an output value of 2. 2 squared is 4. So 2 goes to 4. And we're going to run out of room here pretty quick. But 2 to the power of 4 is +16. So 4 is going to be way up here. It's going to be out of reach here, way up here. So let's not even put this on here. So the graph itself, if we put points in between these, we're going to have, points that line up in between. So it's going to kind of look like this. The more points you fill out, it's going to look like this. So we will draw a smooth curve through those points. And this is sort of what the exponential function looks like. It's not a parabola, right? A parabola, y equals x squared. A parabola looks like this. Okay. So portions of that graph, you might say, hey, this portion right here, from like here to there, looks pretty similar. Kind of. This never curves back up, though. It does not go back up like a parabola would, so this is not quite the same at all. This actually kind of levels out. It starts to approach y equals 0. So that line, here's the y-axis. It kind of goes like this, and it comes down. It gets forever closer. It gets infinitely close, but never touches it. And it keeps getting closer forever. which is a weird thought, but it approaches, so it's called a horizontal asymptote. It's like a boundary that's never reached but always approached. Think about that. Okay? So it's like you walking towards a spot on the earth, you're always walking towards that spot, and the closer you get, the more you have to slow down, because you have to keep approaching that spot for your whole life. So you can kind of get how it's like, I'm getting closer, so I need to slow down. Because A, I can't stop, and B, I can't ever get there. That's what's happening here in the graph. That's weird, eh? Can you imagine having to do that? It'd be like doing this your whole life. Getting closer, but I can't quite get there. You're just like penguin waddling, you know, to this spot that's right in front of you. It'll be right in front of you your whole life. Oh, that's right there. Okay. Random weird thought. Okay, let's move on. Any questions there? You good? All right. So an exponential function generally looks like this. This is the one we just drew. Y equals 2 to the power of x, let's say. You could have different bases. Could be 3, could be 5. The shape will change a little bit. You should notice that, you know, if the base is different, whatever the base is to the power of 0 will still be this point. But the graph might increase quicker if the base is larger. Okay, so that's be a 3 to the power of x, or 5 to the power of x. It increases quicker, and then actually goes down a little bit quicker down over here too. So they kind of change a little bit on both sides of that. Now this one here, you'll notice that the base is greater than 1 for increasing functions. If the base is between 0 and 1, for example, y equals 1/2 x, then it's opposite. It's the other way around. So on an xy table, let's just draw that real quick. I'll give you a few points here. So if I had -1, 0, and 2, and I was going to generate a few points for this graph right here, then what would happen would I'd have 1/2 to the -1, which actually equals 2 to the +1. You see, I'm flipping that now, which equals 2. So -1 would have a value of 2. 0 would be 1 still, so 0, 1. And 2, this would be 1/2 squared, which would be 1/4. So we'd have 2 1/4 over here. Therefore, the exponential function flips, it flips horizontally. Okay, it is decreasing in the similar fashion as it increased over here. But it just flips horizontally. Okay. Now the question, 2 questions arise from this. What happens if c is equal to 1, because 1 is not accounted for in either of these situations? So what happens if c equals 1? Well, if we did a table of values, which I will real quick here. So if x equals -1, 0, and 2, then what is 1 to the power of -1? Well, that's 1 over 1 to the +1, which is 1. Okay. What's 1 to the power of 0? Anything to the power of 0 is 1. Okay. What's 1 squared? That's 1 times 1 is 1. So what you see is you have a horizontal line. This is not an exponential function. So 1 is not included in the base for an exponential function. That's just a constant term. That's the same as y equals 1, right? You get that? So 1 to any power is just going to be itself. So that's the same as y equals 1, not an exponential function. The other question is, what about negative values for c? And just give me a second here. I don't know if I addressed that exactly somewhere. I thought okay, let's do it now. So I do have some notes planned up here, but right now. So what happens if we have a negative value for c? So c is less than 0. So let's say that c is -2 to the power of x. It should be noted that if you type this into your calculator, -2 to the power of something like 4, you're going to get -16. Now why is that? Because the negative is not part of the exponent. It doesn't apply. What I mean is if the base truly is a negative value, it would be like this. So -2 to the power of 4, that's going to be -2 times -2 times -2 times -2, that's +16. So if you have a negative value here, so let me do that again, bracket -2, bracket to the power of 3, let's say, then that's going to be 3 negatives multiplied. We're going to have a negative value. So that's the basis of this table of values here. If the base was truly negative, then the y values start to look like this, where every other y value taken, as whole numbers here, every other y value is going to be negative. So what you have happening is you have something like this happening. You have a positive value, you have a negative value, you have a positive value, you have a negative value, you have a positive value, negative, positive, negative. See that, how it bounces from back and forth? So that's not an exponential function. As a matter of fact, that's not continuous at all. It bounces around. If you tried to graph that on your graphing calculator, I don't think you'd see anything. There wouldn't be anything, because points are indistinguishable on your graphing technology, and because there's not a whole string of points together, you wouldn't see a line. If truly they are separated, I believe that you would see nothing. On some graphing technology, you might see a faint dotted line spanning both of these, right? But that's not a continuous function, so this is not an exponential function. So c cannot be less than 0. It doesn't work. Got it? Yep. So domain for exponential functions is y equals xer. Okay? And that is, of course, where c is greater than 0. And technically, it's not defined as an exponential function if y equals 1. But the range is y is greater than 0. Now, obviously, you know about parameters. You know about, hey, what if we multiply everything by negative? Yeah, there's going to be a reflection. There's going to be flipping. So this is going to change. But for basic, y equals b or c to the power of x, the range is above 0. So when c is greater than 1, we have an increasing exponential function. Increasing. And of course, as I drew earlier, it looks something like this. So this would represent, in a real life situation, something like exponential growth. Okay, if you have a population of bacteria that's doubling every hour or whatever, then this is going to be growing exponentially. If you have money that is, compounding interest, it's growing exponentially. It's not a straight line, it's not a parabola, it's this special sort of exponential increasing function. If you have c that is between 0 and 1, what's going on with my computer here? Then we have a decreasing function, as you saw in the diagrams above. And this would represent something like, exponential decay. So if you have the, decay of some organism or something, the amount of material, if you have, radioactive elements, let's say, so you might represent, some kind of exponential decay by a exponential function that looks like this. So it's getting smaller and smaller over time. The rate at which it's getting smaller is decreasing over time, but it still is getting smaller. So here's some definitions from your textbook. A common application of exponential decay would be half-life, the length of time that an unstable element spontaneously decays to 1/2 its original mass. That's what half-life is in science. So, okay, exponential growth and decay. Any questions? All right, so let's take a look at this from another angle. Let's work from a graph and try and figure out what the equation is. Okay, so right away I know this is decreasing, so my c value is going to be somewhere between what? 0 and 1. Okay, it's going to be a fraction of some sort. Okay, so let's take a look at the values that are given. I have points for x equals -2, and this would be positive 16. Okay. I also have -1 is positive 4. Oh, that's really handy. And 0, 1, of course. Now, I'm not given any points beyond that, but this is enough. So we're basically looking for, y equals some base, because I don't know what the base is, to the power of -2, let's say. And that's going to equal positive 16. Okay. So positive 16. So what number to the power of 2 is going to be 16? So for example, I can just take this negative sign away, and I can say this is an easier one to solve, right? What is this answer? This is 4. Okay. Now, if I wanted some number that had a negative 2 as an exponent, that negative, remember, flips things. So I would need to flip or take the reciprocal of 4. So if I did that, this is what it would look like. And would that still equal 16? Yeah. So now I go backwards. Okay, y equals, my base here appears to be 1/4. Okay. Now let's check a couple other things. Let's check -1. So 1/4 to the -1. Well, that would be like flipping 1/4 and making it 4/1. So this should equal 4. And does that match here? -1 and 4. Yeah, it does. And of course, 0 is an easy one. That's a tough one to determine what the base is, because anything to the power of 0 is 1. But of course, that does work. So I've got y equals 1/4 to the power of x. Everyone okay with that? Good? All right, use your power of reasoning. All right, here's another one. Now I know that c is going to be greater than 0. The points that I have here are going to be 0, 1. Big surprise. It's going to be 1, 5, and 2, 25. So you should be able to figure out what the connection is between a base and something to the power of 1 is 5, and that same base to the power of 2 is 25. Doesn't get much easier than this. What do you think the base is? So what to the power of 1 is 5? Yeah. What to the power of 2 is 25? It's 5. So we have y equals 5 to the power of x. Everybody good with that? All right. Pretty easy so far? You got it? Okay, there's not much more to this section here. So let's just focus on the key ideas that you find in the back of your section there. An exponential function in the form of y equals c to the power of x, where c is greater than 0, is increasing when c is greater than 1. It's decreasing when c is between 0 and 1. It is neither increasing or decreasing when c equals 1. So we know about that. Okay? It's really more of it's a constant function. Okay, so it has a y-intercept of 1. There is no x-intercept. As I mentioned earlier, that line approaches the x-axis and continues to approach forever, but never touches it. So yes, it kind of slows down. The rate at which it approaches that line slows down over time, but it still does keep approaching that line. But it does not have an x-intercept. The range is always y greater than 0, not or equal to, because it doesn't have an x-intercept. Y-intercept is 1, and it has a horizontal asymptote at y equals 0. So remember, the asymptote is a line. It can be perpendicular, it can be vertical, it could be horizontal, it could be slanted or oblique. But a horizontal asymptote would be some kind of horizontal imaginary line where the graph, as x approaches either positive or negative infinity, that the graph kind of snuggles up to, I like to say, kind of gets really close but never really touches it. So a horizontal asymptote would be sort of a boundary or a barrier which the graph cannot touch or cross as x gets extremely large or extremely small. Okay? That's a horizontal asymptote. So questions about this or anything I've said in this lesson so far? Seems pretty straightforward? All right. Okay, you're going to have a good chunk of time here to work on your assignment, 7.1, 1 to 8. Right here.